So, previous two chapters, we're talking about important concept, which is since nothing is moving, nothing is rotating, so we would need to use few equations. Three equations actually, and all of them equals to 0, as long as it's not a couple. It means that when you have force equals to 0, it's not moving linearly. Horizontal axis is not going to move vertically along vertical axis, and it's not going to rotate around a specific location. So we pretty much know those three forces need to equals to 0. However, most of the problem we solve in those two chapters, they're going to be concentrated at a single point. However, that's not always the truth that we try to calculate for mechanics problem. For instance, if you try to open the door, the one in your notes, you use a cable to pull the doorknob. Then in this case, how many forces are we talking about? We certainly have multiple forces, and one other thing is that the force are not going to be concentrated at a single point. If you draw the three-body diagram of this thing, of this people, what we have. What we have a pulling force, right? Because you try to pull everything to this direction, you have another force pulling you back to that direction. That's in the third law. So you have a force over here. Let's say this is X. And this person, certainly he has weight. So let's say his gravity of center of gravity is over here. Then the weight is going to be located at this position. And this one is standing on the ground. And it's not moving up and down. So for sure, what happened? We have a force over here, which is normal. What else? So this cable try to pull this person forward to your right hand side. And obviously, when we are doing something like this, we're not going to move. So in addition to the force, horizontal force over here, we actually have another friction on our foot that prevent us from moving. So which means we have another friction over here that prevent us from moving. So with all those forces figure out over here, those two forces equals to 0 again. How about my moment? So if we say I want to do the moment around my gravity center, what does this equals to? Is this person rotating around here? No, obviously not. So it must equals to 0. Is it rotating around the cable? No. Right? Let's say this point is C. And the moment about C is 0 as well, because it's not, this person is not pointing down. So obviously, it doesn't matter which point you use as your moment center. The moment equation around that, any point on this person should equals to 0. It also implies we have two equations over here, which means we can fulfill the problem, which is two unknowns, right? If you use one additional equation, then you can get up to three unknowns. Sometimes, in this kind of problem, you might have more than three unknowns. In that case, we certainly want to use those two equations because there are no moment arms included in those two equations, so we definitely want to use those two. But if you have additional unknown in your system, you might want to use two moment equations. So in that case, you're going to have four equations to deal with four unknowns. That will somewhat simplify the calculation. But there is one thing you need to be careful. Sometimes, even though you use two moment equations, and it can be redundant, which means this the number in this equation is actually some kind of scalar of this equation. If that's the case, you need to find another reference point to come up with your moment equation and still deal with four equations with all the unknowns. Okay, so rich body is nothing but talking about things like this. However, when we are dealing with the free body diagram of rich body, there are a few different kinds of things. What are they? Okay, so in chapter 4, we have one specific example. In that example, we have three forces applied to it. But I would like to replace this one with a force moment system. What happened? Something like this, right? So if that's the case, it means that sometimes we might need to know what happened at the contact point, so that we know which kind of free body diagram we should use to deal with the balance of the force here. So there are different types of force. If you have your textbook in chapter 5, you should be able to find those information. But if you don't have those if you don't have your textbook, you just have the notes. There are something you need to know when you try to solve the problem in this chapter or the next few chapters. One, if this contact is like a ball, what do we have? It's going to be normal force. So in this case, if I have a structure like this, the free body diagram at this point is going to be a single force. Let's say this one is upward because it's perpendicular to the contact surfaces over here, between those two contact surfaces. Okay? If it is fixed end, like this is a cantilever beam, and we have a free body diagram like this. So typically, we would need to assume three things: two forces, Fx, Fy. It doesn't matter how you get that. I would, if you don't really know the number at that moment, I would always use positive direction as my assumption, because that will be easier for us to determine or understand which direction it actually moved to after we get the numerical answer. Because if it's negative, it means that it's not toward to your right hand side, it actually goes to your left hand side. If it's negative in the vertical term, it actually says positive upward, negative downward. So over here, there is one other thing you need to know. Moment. Okay. Again, I would like to assume it's counterclockwise because numerical-wise it's positive. So when we are dealing with those kind of things, if it's fixed end, we would need to attach three things at the end over here. Okay, fx, fy, and m. The moment, all of them should be positive. So if it's something like this, and this is fixed at the bottom over here, obviously this one is rotatable, which means this is not going to fix the bar or the member attached to this joint. In this case, but obviously when this bearing is located over here, the joint over here is not going to move horizontally or vertically. So in that case, we're going to draw two forces in x direction and y direction, but we're not going to draw the moment at this joint. Okay. So after doing that, you still need to add the force into your free body diagram, your equation of equilibrium, and solve for the force at the supporting joint. Okay. Those three are the most common types that we're going to use in this class. There is one other thing you guys will need to know, which is cable. Cable is a very specific. So when this is the cable attached to the object over here. So if you draw your free body diagram, what kind of force you're going to have? Are you going to have a pushing force if this is the cable? Is it possible to use a cable to push something? No, it's not possible. So the only force is what? Pull. So when it's a pull, it's a single force, parallel to the direction of the cable. Which means if you have a cable attached to here, is it possible for you to have a force in this direction only? No. You might argue that you want to do something like this. Well, you can do that, but I wouldn't suggest you do that because in that case, how many unknowns you're going to deal with? Two, right? One in horizontal, one in vertical. It will create some issues when you are doing the configuration. The more unknowns in your system, the more mistakes you're going to make. So probably that's not a good idea. We will still want to deal with something like this as your free body diagram. So those are the important things that we need to know as when you draw a free body diagram for a rigid body. Any questions so far? So those are the four important things that we actually use in this chapter. There are a few more types that you can find in the note. You can find in the notes or in the textbook. Sometimes this is not something like this. Sometimes you will say it's a ball. When it's a ball, it's the same representation. Sometimes you're going to see there are rollers under the connections over here. In that case, they are the same. So there are different representations like this. For individual ones, just be sure you know how to read the configuration and draw the correct free body diagram. That's the most important thing for this chapter. One of the most important things for this chapter. Okay. We're going to talk separately then. So if we want to draw a free body diagram for this thing, so obviously, when you put a ball in a slot, you're going to have two contact points at the ball. One is here, the other one is here. So we have two locations. How are we going to generate our free body diagram? Since this is the ball in real environment, we of course are going to have weight. So the weight is located at the center. Normally we assume the force is going to be at the center. So we have weight over here. And the other one is, we know this is 60 degree, which means the force at the contact surface is what? Perpendicular to the surface over here. So we have, let's name this one RA. Perpendicular to the surface, which means the angle over here becomes 30 degrees. Okay? Now, over here, that's another contact surface over here. Okay? We will need to have that perpendicular to the surface, which means in this case, RB is going to have the angle. This part is 12, this part is 12. Okay, based on the configuration over here. So that completes your free body diagram. We probably doesn't need to deal with any moment equations over here because we only have two unknowns, RA and RB. Most likely the weight is going to be given. So in this case, you don't need to use any moment equation to come up with the answers. Okay, and that is going to be your free body diagram. Any questions? Yeah, another one. So I'm not going to solve this problem. I'm just going to draw the free body diagram for this thing. So over here, how many connections we have here? Okay, 3. So that's what is this? Let's name this one. So let's start from point A. What kind of free body diagram we should use at point A? Since this is a bearing, are we going to have two forces, one in x direction, one in y direction, and the other with a moment, or we just need to consider the force configurations? Do we need to worry about the moment? No, because this is a pin connections. So over here, I would like to use AY and AX. Again, I assume both forces are going to be positive. That's just for my own convenience, because if it turns out to be negative number after doing the calculation, it means that I'm assuming my assumption of the directions are wrong. But other than that, the calculations are all correct. Okay. Now, how about B? what kind of forces we need to deal with at point B. One force, two forces, or two forces with one moment. One force, what kind of force, which direction we're talking about? Upward, horizontal, upward. Okay, we have a connection at C, which is a cable. So, as a cable, what kind of force are we providing? Pulling or push? Pulling. So when we say it's pulling, is that downward or upward? Downward. Do we know the force over here? Why is that? Okay. Other than that, do we have any other force we need to consider? The weight of the bar, of the beam. So, if we assume this is homogeneous, where should we put the weight? Center. So, this is the total length for this beam is what? 600 millimeter. When we say it's going to be at the center, it needs to be 300 meters away. So, it probably is something over here. Okay, so that will complete my free-body diagram. So actually, I'm dealing with 1, 2, 3, 4, 5 forces based on the configuration over here. Any question? So let's do one of example which is similar to this configuration. So far, all the solving procedures is going to be the same as what we did in chapter 4. The only difference that we're going to have is how we draw the free-body diagram, because in chapter 3, chapter 4, the free-body diagram all concentrated at the same location. But over here, they're not. So when you are dealing with the moment equation for the configuration in this chapter, one of the most important thing you need to identify is the distance between all the forces. If you fail to identify those distances, your moment equation can be wrong. So be careful about those configurations. So, the example that I would like to talk about is A, and this point is B, the distance, over here, so the beam is subjected to a uniform load and a concentrated load as shown. So one here, determine the reactions at the supports. So I would need to know the forces at this support and this support. So we are given two forces, Y, support, we have, based on the procedures we defined in the previous chapter, the first thing, after identify what are given and what we need to find, the next thing we need to do is to draw the free body diagram of this specific configuration. So to do that, let's draw the given forces on top of this free body diagram. First, this is A, this is A, this is B, let's assume this is C. So this is 30 kilonewton, this is 26 kilonewton. What else we have? What kind of forces we need to take care at point A? One force, two forces with a moment. Which one? Two forces. So over here, I would like to use AX and AY. And over here, B, we would like to use DY only. Okay? So when we have the configuration like this, how many unknowns are we actually dealing with? 3. So obviously, 2 equations is not enough to deal with a problem like this, right? So I would like to start writing down those 2 equations and worry about the moment equations later. So for force equation, we have AX towards to the right hand side, which should be positive, and we have 26 kilonewton. This is 12. This is 5. This is going to be 13. So horizontal force is going to be 5 over 13. So, but in this case, it's going to be positive or negative. Negative, right? What is this going to equal to? 0. Very good. How about here? We have AY. Since it's pointing upwards, so I use this one as my positive direction. And BY is positive as well. But we have 2 other loads, which is 30 kilonewton located over here. And we have another force created by this 26 kilonewton. That is going to be 13 over 12 because it's the cosine value of this angle. What does this one require to equal to? 0, right? So far, any questions? No? However, we should be able to get AX straightforward because one equation, one unknown. We should be able to get AX equals to 10 kilonewton without any problem by using this equation. But can you solve AY and BY based on a single equation over here? No, it's very unlikely, right? Because we have 2 variables and 1 equation. Logically, we wouldn't be able to get the answer. So other than that, we say we need to we can use moment equation to deal with the additional variable. So in this case, we would need to use moment equation. But do you want to do point A or point B? It actually doesn't really matter. Personally, I would prefer to take point A. The reason is because this is at the end of the cantilever beam, so you don't need to worry about how much distance we're actually dealing with. If you use B, then you need to know the distance between 30 kilonewton and the point B. You need to know 26 kilonewton with B. So sometimes you guys may make a mistake because you try to figure out the moment of individual forces. In addition, when you are dealing with the moment at this position, the direction of the moment created by the force is going to be different. Because in this case, 30 kilonewton is going to be clockwise, rotating around point A. But if it's going to be B, it's going to be positive around point B. Though the result should be identical, but in order to not confuse when you are doing the calculation, I would suggest you use the point at the end. That will save you sometimes. And the other way of choosing the variable is the reference point is if you has a point which include most unknowns, use that one. Because if you are using this one, AX, AY, both of their moment arms are what? But if you, let's say this is something like this, okay? If you say you want to do the moment center at this point, what happens? Both AX, AY are going to create moments because, and what's worse is AX, AY, they are all unknowns sometimes. So it make that in this scenario, your calculation might be a little bit complex. So I wouldn't suggest that. I would always use the location where most unknowns is located, because the moment arm is 0. Okay. But anyway, in this case, we're going to have 30 kilonewton multiplied by 1 meter clockwise, so it's going to be negative. And I have dy. The moment arm is 2 meters. In this case, it's going to be positive because it's counterclockwise. So I have a positive sign in front of it. I also have another force 26 kilonewton. You need to decouple this force into horizontal and vertical and test the moment independently. But in this case, you're going to have one vertical force over here, one horizontal force over here. Which one is going to create moment and which one is not going to create moment? Vertical force is going to create moment, but the horizontal one is not going to create any moment. So the vertical one is going to be 12/13 because it's a cosine value. What is the moment arm in this case? 3 meters, right? Is this positive or negative? Negative, right? What does this equal to? Is this cantilever rotating around point A? No, so it's equals to 0. How many unknowns we have here? Just one. So we can solve dy equals to 51 kilonewton. You can plug this number back into this equation and get the answer of AY. If you do that, you're going to find AY equals to 3 kilonewton. Mark the answers so I know what you get. Okay, so that is going to be the answer for this specific problem. Any question? Is that clear? Everybody understand what I'm talking about? We're going to talk about another example, and I'll let you guys have a short break.
Real quick about that problem you did. There was some forces to the Y. Are you unable to use your 10 kilonewtons from your never mind. I got it.
Okay. Okay. If you have a question, let me know. Okay. so this is the configuration of the next example. A bracket ABC is supported by a hinge at point A and a roller at point C. Determine the reactions at the supports due to the loading shown here. So this is A. Okay. So we still need to identify what are given and what we need to find. So we are given two loads. One is force 750 pounds, and the other one is actually a couple or a moment, you name it. So we want to find reactions at A and C. Then we need to draw the three-body diagram. The 750 pounds is the first thing I would like to draw here, because that's the only numerical number that we get. Straightforward. And the second one is it's going to be here. 1,000 pound-foot, which is a couple over here. So I have two supports in my configuration. Point A, what kind of supports are we going to use here? Is this fixed end, or this is a pinpoint, or this is a contact surface? Pin, right? So when it's a pin, what kind of a configuration we have here? Two forces. One is AX. If you still don't remember what we have here, please refer to the notes in the beginning of this chapter. When it's a pin, it's always two force. If it's a fixed end, it's always two force plus one moment. If this is a ball or simple contact surface, it's going to be a single force perpendicular to the surface, which means this one over here is going to be perpendicular to the surface. And we also need to identify the angle. So over here, it's going to be 3, 4, 5, because this one is rotated for 90 degrees. So that's the reason why we get the 3, 4, and 5 in this configuration over here. Does that make sense to everybody? Okay. So after you finish your free-body diagram, there is one important thing I would like you to do. That is to draw the direction of X and Y. In this case, you ensure yourself which direction is positive and which direction is negative. Okay? Because sometimes you might confuse yourself and don't know whether this is positive or this is positive. So if you have a reference coordinate over here, you always ensure yourself right hand side is your positive, left hand side is your negative. Okay? Does that make sense to everybody? Questions so far? Is that clear? Everybody understand how I draw the free-body diagram? Okay. If there is no more questions, the next what we're going to do is figure out the equation of equilibrium for everything. First, I would like to use the two forces in horizontal axis and y axis. If it's x-axis, it's going to be 750 pounds plus ax. Now I have a supporting point force over here. It's going to be let's name this one FC. Okay, so it's going to be FC multiplied by 4 over 5. Is this positive or negative? Negative, because it's forward to your left hand side. So over here, this equals to 0. Is that clear? Everybody understand what I'm talking about? Okay. So vertically, we have AY. We have FC multiplied by 3 over 5. In this case, is that positive or negative? Positive. Sometimes you might think this should be negative because both of them are negative, and the configuration are those two equations. Now, the other equation that we would need to come up with is the moment equation. As I said, I would like to use the position that has least, as the most unknowns. In this case, which point we actually has the most number of unknowns here? A, right? So I would like to use A as my reference point. So if we do that, we have this one is kind of a given, so you don't need to worry about the moment arm. You just write down 1,000, but be sure you put the correct sign in front of it. This is the what? Clockwise. So when it's clockwise, what do we have? Positive or negative? Negative. Very good. So we have 75 pounds. The moment arm in this case is what? 2 feet. So in this case, is that going to be positive or negative? Negative. What else do we have? We have FC. FC is going to create moments in 2 directions: horizontal force, vertical force. So we would do that accordingly. So if we have the horizontal force, it's going to be 0.8. Let's do that. 4 over 5 FC. That's my horizontal force. If it's a horizontal force, what is the moment arm? Is that going to be 8 feet or 3 feet? 3. This is a horizontal force, so it's going to be 3. 3. Is that going to be positive or negative? Positive. How about the vertical force? It's going to be 0.6 or 3 over 5 FC. And what is the moment arm in this case? 8. Is this going to be positive or negative? Positive, right? Equals to what? 0. So how many unknowns we are having here? Just 1, right? Just 1 FC. So if we do that, we actually can get FC equals to 347 pounds. So clearly, the first 2 equations over here are related to FC only. So if you plug this number into fx and fy, you should be able to get ax and ay. Very straightforward. So if you do that, you're going to find your ax, ay is going to be negative 0.6 FC or negative 208 pounds based on this equation. If you have this equation, you actually get ax equal to 0.8 FC minus 750, which equals to negative 472 pounds. Okay. What does the negative information tell you? The direction over here is what? Opposite. do I do any mistake numerically wise? No. So if you see it's negative, just leave it there. As long as I know your assumption over here is both of them are positive, you'll be fine. After you get in this thing, don't try to change the configuration over here, because if you change that, it means that your calculation is somewhat wrong. Okay, you would always assume over here is positive. If you want to change everything in your free body diagram like this, you would need to give me numericals number with the correct directions. Okay, if you don't intend to change anything over here, just leave the negative sign in front of it. Okay. Any questions so far? Okay. Not. Then we're going to move on, which is we're going to talk about force vectors. So when we have a two force member, what does that tell us? So if I have a bar, I have two forces like this applied at both ends. So when you start to pull, there is no supporting in between. When you start to pull, what happens? This thing is going to align to the direction of the force you apply onto it. Okay? So it's going to be the same. When you have two forces over here, what happens? This one will start to rotate, right? Until it becomes something like this. Right? You guys have like an experience like this. If you pull both ends, it actually becomes something like this. Right? When you have something like this, it follows a specific physical condition, which is if you connect, you draw a line between the two forces, those two forces are actually along the same line. Which means it doesn't matter what kind of geometry shape of your component, this rule applies. Okay? So when you start to use two forces to apply onto a specific object, when it's not rotating, it's not moving, the two forces are actually on the same line. Which yield a very important thing, which that is if you have something like this and you apply force over here and over here, do you really know? This is not a good idea. Okay. So you have big structure. And you would like to analyze the force over here for this specific bar, and then this bar A and B. Where are the forces has been applied? They are only applied at both ends, A and B, right? So for this bar, what do you actually feel? You only feel two forces located at both ends. So it means that it's like this bar has only two forces, it doesn't matter. The force is actually a combination of 3 bar applied to this joint. It doesn't really matter. For this part, it just feel I have two forces at both ends. So with that information, this is the two force member. When it's two force member, I say it's going to be aligned to the force. With the orientation is going to be aligned to the how the force has been applied to it. So in this case, we actually know the direction of forces applied at A and at B. That's the physical configuration of two force member. Okay. So in other words, if you know it's a two force member, and I'm giving you the direction of the object, it also implies you know the force, the direction of the forces at both ends. That's how it's going to look like. Does that make sense to everybody? Yeah. Two force member is common in chapter 6 when we're talking about structure. Two force member is actually everywhere. So that is something I would like you to know beforehand. Other than two force member, there is another thing, three force which means in this case we apply three forces on a specific component. So the example you have in your notes. When you have a three force body, all the forces are going to point to the same point. For instance, over here, you know the configuration of A. Over here is going to be AX and AY, right? Nothing fancy. We also know the force at B is going to be a single force which is perpendicular to the contact surface. But before you do the calculation, do you actually know the direction, the angle of the force located at A? Probably not, because over here, only when you get AX and AY and use the tangent number, inverse tangent to calculate for the combination of those two numbers, you know the angle. But if this is three force member, we can actually ignore that part. What I mean is, you can extend the line of this force, extend this line of the force. They are going to be intersect at a single point. That also implies the force provided at point A is going to be intersect at the same point. So if you draw a line over here, that is going to be your FA. Now you can say I want to do Fx and Fy independently and solve for that. Well, that's sometimes easier, but if you are if this component only have three forces existing on it, you can actually use a combination like this to come up with the answers. Does that make sense? But for a three force body, there is one important exception, because we say it's going to, if you have only three forces applied to a single body, they're going to be intersect at a single point. You can say it's always true, and you can say in some cases it's not true. The case you're going to encounter is if you apply force in the middle, or anywhere over here. Okay, so when you have R1 and R2 that are supporting the roller on the cantilever beam, are they going to intersect with each other at a single point? No. Why? They're parallel. There is no horizontal component involved, so the only thing you need to deal with is y equals to 0. And you might use small equation to find out R1 and R2. So in that case, all the forces are vertical force, right? This is the only exception you're going to encounter for a 3-force body. If your 3 forces in the component has x component and y component, both of them, then they must intersect at a single point. But if those forces only have horizontal or vertical forces, then they're not going to be intersect because they're going to be parallel with each other. The reason I say they still intersect with each other is that if you draw the line, what is the definition of parallel? Are they going to intersect? No. But in the definition, in your calculus or whatever, it will say the two parallel lines that they're not going to intersect within finite distance. But if it's infinite distance, they're going to intersect. It's really not going to intersect, but the definition applies here. So we have 3 parallel forces. They're going to be intersect in infinite distance. That's something we're not going to violate the definition of 3-force body. Okay, they're going to intersect in the infinite distance, but in reality, when we are doing the calculation, they're not going to intersect. Okay, does that make sense to everybody? Somewhat. Okay, let's work on one of the examples. This example is a little bit tedious. Let's do the first example next time. I'll do the second example. So I have a weight of 200 pounds hangs from the frame with ignorable weight. If the frame is in equilibrium, determine the loads acting on frame at A and at B. Okay. You can use the regular configuration. Fx, the 4 forces located at A and B. They are Fx, Fy, Fx, Fy at A and B, and try to solve for the unknowns. That will work because it's not really difficult to deal with those kind of things if you decouple everything and understand what's going on over here. But I would like to use 3/4 member to solve for the problem over here. So why I say it's 3/4 member? For the bar ABC, how many locations we actually have force applied onto it? This one, this one, and this one. Right? So let's define what we're trying to find. We are given a 3/4 body. We would identify FA and FB. that's going to be the case. What are the three forces are actually coming from? So, do we know the direction applied at point D? Do we? How many forces apply to the bar BD? Two, right? One is at end B, the other one is at end D. So this one is what? Two force member. So when it's a two force member, do we know the orientation of the force applied at B and at D? We do, because it's parallel to this thing. So we know this is 3 feet, this is 3 feet, so this is what? 45 degrees. Everybody agree with me? So since we know this is 40 degree over here, 45 degree over here, can you determine the force applied at point D? We do, right? Because two force members. It's going to be like this. This point is D, this point is D. So far, does that make sense to you guys? Now, since we know it's going to be the case, we also know this force over here is what? 200 pounds over here. And we know at point B it's going to be the same thing, RB. Going to have an angle over here is 45 degrees. Right? Now, based on the configuration of three body force, I should be able to determine the force of RA. So if I draw the extension line of the forces, those two forces obviously is going to concentrated at this point with the angle equals to 45 degrees. Right? So if you, and we also know there is another force located at point A. If you draw the extension line, make them intersect at the same intersection point, we actually know the direction of RA. Does that make sense to everybody? That's the definition of three force body. So the rest of this problem becomes geometry method or geometry configuration, which means I know I have what? 200 pounds vertically. I know degrees. And the length over here is what? RD. I also know my RA is going to be something like this. So based on the geometry method we learned in chapter 2, the configuration is going to be something like this. So we have one angle which is known. We know this is 45 degrees. Do we know anything else? At this moment, no. Right? But based on the configuration over here, is it possible for we to figure out the angle over here? Yes, because we know this is 3 feet. We know this is 45 degrees. What is the distance over here? 3 feet, right? Do we know the distance of this part? Yes, we do, because it's in the middle. So this is 3 feet. So do we know theta over here? Theta is going to be arctangent 3/6. Or you can actually get this number (26.57 degree). Everybody with me so far? Get this angle. So the angle is actually over here, right? This angle, if you draw a parallel over here, they are the same degree, right? So if you add 90 degrees to this one, we can get the angle over here. That is going to be 90 plus 26.57 degree, which means the angle over here is going to be 116.57 degree. Does that make sense to everybody? So we know this is 45, this is 116.57 degree. What do we have over here? 180 minus this number, and we get this angle, which is going to give me 18.43 degree. How many angles do we know here? 3 angles. How many forces we know in this triangle? 1. So what do you want to do to find out RA and RD? Log size. Very good. So we can use log size. I know my 200 pounds is corresponding to 18.43 degree. So my RA is going to be corresponding to 45 degree. My RD is going to be corresponding to 116.57 degree. So with log size, I should be able to calculate for all the forces in this triangular configuration. So you're going to find RA equals to 447.33 pounds. RD equals to 565.8 pounds. And those two are my answers. Does that make sense to everybody? Is that clear? So sometimes you might say, okay, this is not so convenient to me. I would like to use XY configuration. That's fine, because personally I prefer it that way. But sometimes you would feel, okay, if you decouple everything into fx and fy, it might be a little bit tedious, and chances that you might make some configuration wrongly. So geometry method or three-force body method is easier for you to figure out what the forces are applied to a specific location. Then you can use the skill I'm showing here to get all the numbers. But I really don't want to force you guys to do geometry method when you have a lot of things, because there is one major drawback is that sometimes it might be difficult for you to figure out whether this is three-force member or it actually not three-force member. Sometimes it becomes four-force member. When it's four forces, they're not going to intersect at a single point. So when they are not going to concentrate at a single point, it's very unlikely you're going to use those iso or cosiso kind of handy tools to come up with the forces. So only when you are very positive, sure the object is 3/4 member, don't use this one. Okay. I need you guys to solve that in the exam, I'll be specific. Okay. Other than that, I would like to ask you guys, if you have 4/4 member, can you use the same skill to determine the direction and magnitude of a force? Can you do that? No. You can do that for 2/4 member because they are aligned to the same line. You can use 3/4 member, 3-body component skills to do that. But if it's more than 3 forces, don't use geometry method.
Can you take that 3-body diagram, and if you're not going to use the geometry method, if you're going to use the other method, can you break it up into the second diagram that you have where you only have the one? Yeah, can you sum your forces and moments from that?
Yes. Yes. You probably want to do because if you probably want to do your moment center at this point because over here you have 2 forces, but one of them is not going to create any moment because Rx is not going to have any moment contribute to the configuration over here. Okay. That's a good question. Any other question? No? Okay. So